All right, today we'll be going over the paper and implementing it in TensorFlow Quantum. And the paper is evaluating the noise resilience of variational quantum algorithms, published last year, 2021, in the journal Physical Review A. As always, I strongly encourage you to read the original paper and follow along. The APS version and archive version are linked below. So getting into it, this is sort of an empirically really straightforward paper, I'll be honest, and that's a good thing. I think papers that are easy to understand are often the best, and so there's some neat results in here. So we want to start off by looking at what exactly is the problem situation. And so if we have our variational quantum algorithm, right, we're trying to minimize some cost operator of our parameters. And so in the paper, they use this trace functionality where we have the trace of the operator acting on the density matrix. This is equivalent to this form, right? This is just the expectation value of this operator given, this state. You can do this. This might be a mixed state though, so this notation can get a little confusing, but basically this is just the expectation value of that operator. And we have this density matrix rho, although it looks just like P when I write it, so it doesn't really matter. That is parametrized, right? These are the parameters that we're learning, which has some noise channels, which we're going to represent with this little Greek letter, I think is capital delta. Let me look it up, delta Greek. Now that I say that, oh, that's not capital delta. Let me find out what Greek letter this is. It is capital lambda. Okay, well, that wasn't really important, but I'm glad I know that. Capital lambda here, right? So we have some set of unitary operations being applied onto this, I should say unitary noise. Noise operations are not necessarily unitary. You could have some sort of noise that measures your circuit, and measurement is not a unitary operation. And so this is sort of, right, this is what our density matrix looks like. And this is just, a fancy formalism for you're applying your circuit and there's noise. That's all this means. And so now we're going to consider some empirical results where we're going to be focusing on VQE. So in this first section, I'm going to go through all the paper aspects first, then we're going to get to the code. In the first section, we're going to look at the simple Hamiltonian for 2 qubits. That's this Z1, Z2 plus ZX1, X2. So a simple Hamiltonian, 2 qubits, and there's going to be 3 circuits we're looking at. I'm not going to draw them out. If you're following along in the paper, you can look at figure 1 as a reference. And those are the 3 circuits we're going to be focusing on. Basically, each of them has rotation Y gates, C0, followed by noise gates, and then either 1 or 2 RY gates before measurement. And then we're also going to work with a 4-qubit system, which has a layer of RY gates entangling C0s interspersed with noise, followed by a layer of RY gates, and this is figure 3. So that Hamiltonian, oh, by the way, this 2-qubit Hamiltonian is given in equation 13. The 4-qubit Hamiltonian is given in equation 14, both of them under section 3. And so now we're going to look at recreating the big figures from this paper, or at least what I think the big figures are, which are figure 2, figure 4, and figure 5. Specifically, though, we're just going to be looking at the energy landscapes. There's also fidelity and concurrence, which is a measure of the eigenvalues of the density matrix. But the reason I'm just looking at energy is, well, I'll be honest, because it's the easiest to work with in the way I did it. And you can work with density matrices pretty easy if you use the Circ density matrix simulator. You can get the density matrix at the end, but I just did not really want to do that and deal with that. So I'm just looking at the energy levels. All right, so now you can see that sort of, it's been pretty brief. That was 5 minutes of background, but that's all there really is to this paper, right? We're going to be looking, okay, given this information, how do the types of noise affect these different circuits, right? Because that's what we want to know. We have noise in our circuits. What can we do to best prevent this noise? Or best not prevent it necessarily, but adapt to it. So we're going to look into that right now, and we're going to see right away that the redundant parameters seem to be important, or sort of over parametrized, right? Where a circuit, in absence of noise, that is simpler, is able to reach the minimum, but is more quickly susceptible to noise, which sort of intuitively makes sense, right? If you have less parameters, they intuitively seem to each one matters more, but that's not really a rigorous mathematical proof. So we're going to get into this right away. First thing we're going to look at is this, I gotta switch over, is the 2-qubit example. So once again, working with TensorFlow Quantum, we have our standard imports, TensorFlow Quantum, Circ, NumPy, etc. So now we want to write up our sort of system to generate this figure. So the first thing we need to create is our circuit. So we have our Y gates followed by our C0 gate. Then, and this is something I don't think I've actually covered before. I was planning to do this more rigorously, but this will do for now. In order to add noise, ever since the TFQ 0.5 release, noise has been supported. You can do noise in these models. You can simply add this channel, right? Either phase, amplitude, depolarizing. There's a bunch more that you can add if you look on the documentation. You can specify basically the probability of this noise occurring, and then what qubit this noise is happening on. And so we insert sort of a noise layer here, and then depending on which version of the circuit, we input different rotation gates. So then to create our model, we simply specify, once again, the standard inputs of data type string. Now this is the different part, which I don't think has been covered before. We have to create a noisy PQC object. And this is, you can simulate noisy things with PQCs. I'm pretty sure if you use a different backend, if you use like Circ density matrix simulator. But this uses the QSim backend, which is pretty fast. So that's good. So I just arbitrarily pick 500 repetitions. We could do more or less. Sample base that just evaluates how this expectation value is estimated, and then parameter shift differentiator. We create our model, optimize it, exact standard sort of optimization techniques. We iterate through them. We get the energy. We use the gradient tape to minimize this energy by using our optimizer to apply the gradients. If it's beneath this tolerance, then we stop and we return the minimum energy. So this is all just sort of, you would see this code. This is just sort of normal TensorFlow code right here. So now we want to create our actual experiment running. So we have 2 qubits here. We have 3 different noise channels we're evaluating, which are the columns of that figure 2. We're plotting 40 different gammas in the range 0 to 1, right? Because this is a probability. Then we have our A, B, and C type circuits with 3, 3, and 4 parameters respectively. This is our Hamiltonian. Remember, is ZZ plus X plus X. And we're just using atom. So now we iterate through all of these possible combinations, create our circuit, create our model, optimize it, and then we repeat this twice to get a more sort of statistically valid not that that's really that great. You could do this 3 times. I think they do it more in the paper. And so you can get the results, and then we just plot them. So when we do that, I will open up what that looks like right here. So this is a result. So if you're comparing, this is row 1 of figure 2. You'll notice it does look a little different. Part of that is I'm not doing a scatter plot. This is a line plot, so I guess that's just different. There's also a little more noisy. They probably did more repetitions. Oh yeah, they said they performed 20 different local optimizations, which is, this took a little while. I mean, not a while, it took like, I don't know, 15 minutes or something, but I don't want to wait, an hour and 30 minutes of running this on my laptop. That I don't want to damage my laptop by running so much code. But anyway, this is the sort of outcomes you get, and you'll notice it's pretty much the same as figure 2. So if we look at this phase dampening, for example, this is all of them start at the minimum of just around negative 2.25 or something like that. And the C circuit, which has the most parameters, goes up the slowest, which means in the presence of increasing noise, it remains the most accurate, whereas the other two increase more and more. And you'll notice in their figure, they cut it off at about negative 1.6, so about here. And so you can see how this orange line diverges even sooner than the blue line. And I think that's just a result of the Hamiltonian choice, not of a result of the noise, because the noise is symmetric on the qubits. Then we see amplitude dampening, and the trajectories look similar. However, one thing to note is this jagged area. They plot the sort of noise independently, like by doing a scatter plot. So you'll see they have a trajectory. Can you see my cursor? I don't know if my cursor is visible, but if it is, wait, no, I don't want to zoom in. How do I zoom out? Okay, there we go. Okay, well, I don't know. Okay, there we go. You'll see this is why this is an average that looks so jagged, is because it's sort of taken between those two runs. And then for the depolarizing noise, you'll notice it looks like they just ran at once, but that's because they're all on top of each other. And you can see they're all on top of each other here. You'll also notice there's a slight decrease here, and I'm not entirely sure what that's from, but I suspect it's simply a result of the local optimization, sort of just a fluctuation, basically. Right, because this is like depolarizing noise 1 is like completely noisy, so I think that's just a function of it. But you can see overall the graphs look very similar, albeit not as pretty. So now we're going to look at generating, if my computer loads, figure 4. So over here we have figure 4 generation, which is the 4-qubit Hamiltonian. Once again, same sort of imports. However, now we have a slightly different circuit. We have a set of RYs, C naughts, followed by noise, another C naught followed by noise, another C naught followed by noise, and then the ending RYs. The create model, optimize model are the exact same code. In fact, I just copied it. This is basically the same, except for it's easier. We don't have a variety of circuits we're changing. We just have noises and gammas. However, it's a 4-qubit circuit with 8 parameters this time, so it's a lot bigger. We create our Hamiltonian, which is just specified in equation 14 of the paper. Very easy to generate in this TensorFlow quantum setup. And then this code is basically the same, and we just run it. And this seems all really simple, right? And that's what's nice about this paper, is there's some interesting results, conceptually pretty simple, and in code pretty easy to do. So if I open this up, we can see I didn't feel like, I guess, refining the names, but you can see figure 4A is basically what this looks like. You can see I also averaged rather than plotting different runs, but once again, the symmetric depolarization results in this energy. I forgot to label this accent energy and gamma, of course. The energy becomes incorrect because depolarizing, right, is a chance of this sort of any sort of noise, which is bad, whereas amplitude and phase dampening are specific kinds. So this is sort of more general noise, whereas these two, right, they sort of plateau off where past a certain point, it doesn't matter how much noise you add, it's still performing the same. So this indicates, right, if you had to choose a type of noise to have, it seems like this phase dampening, at least in the case of this Hamiltonian. That might just be because of the Hamiltonian, you know, maybe you want to write some results, try this with different Hamiltonians. And then the last thing we're going to look at is figure 5, which just shows how this sort of optimization landscape can get fudged by these parameters. So here, what we're doing is we're just, rather than saying, okay, we're evaluating the noise at different gammas, right, or different, you know, probabilities of this noise occurring, basically different noise levels is what we've been doing before, right? We're plotting the noise level versus the energy, or basically how well it's performing, and the lower the better. I don't know if that was clear before, but right, the lower the better in all of these, and this is increasing noise, better performance is the green line, just to review that. Once again, green line here this time represents the type of noise, increasing gamma static circuit. Now here, we look at the parameter landscape for a single qubit operation, Ry, followed by a depolarizing channel, followed by Ry. Then we run this output, and we basically plot this over a number of potential thetas, theta 1 and theta 2s, or parameters, the two parameters here. And then we also run this without noise, and we compare them side by side. So this is figure 5 right here. You can see that the landscape is very smooth, right? Look at these lines. This is probably like the best created. I mean, I try to create it exactly. If you look at the figure, they have that gold and blue color scheme. I couldn't find that in Matplotlib. So I tried to, I looked at the color schemes. I didn't find it. So I tried to recreate exactly, but this is probably like the best I've ever recreated a figure from a paper, in all honesty, is right here. Look, like that's exactly what it looks like, which is nice. And then we can see over here, you know, if we're sort of optimizing from here to here, it's very smooth, but over here, there's a lot of noise. And you can see how this can hinder the optimization landscape. So that was pretty quick. Here are the 3 results. There's more figures in the paper. Figure 7 is pretty important. Figure 10 looks really cool, but I didn't work too much with the fidelity concurrence operations. So this is sort of the first, I guess, parts of the paper. You're welcome to try all the other parts of it, but hopefully this is sort of a good review. It's a short, you know, clever little paper, I think. That's totally meant as a compliment. It's great, because it's, you know, easy to understand, easy to implement, which is always a great thing. So as always, you can find the code and the everything linked below. Check out the original paper. I referenced a lot, probably more than I usually do, so make sure you're following along. And that's all.